With its nearly infinite recyclability, aluminum is one of the rare materials of which about 75% ever produced has never truly disappeared, but continues to exist to this day. So how can a seemingly discarded piece of aluminum be reborn without losing its quality? That journey begins with careful collection and sorting, where impurities are removed before the material is shredded into smaller pieces. It is then melted at high temperatures, returning to its pure liquid metal state. From there, the aluminum is cast into ingots, rolled into thin sheets, or reshaped into entirely new products, ready to enter a new life cycle, almost as pristine as it was in the beginning. Today, Agriculture Insight invites you to explore the remarkable rebirth of aluminum, a cycle with almost no end, where waste is simply the beginning of a new return. Aluminum is one of the most abundant metals in the Earth's crust, accounting for about 8% by mass, but it does not exist in a pure form. Instead, it is always locked within ores. Before the Hall-Héroult process was introduced in 1886, extracting aluminum at an industrial scale was nearly impossible. As a result, production costs were so high that the metal was once considered a luxury, even more expensive than gold. A striking example, Napoleon III used aluminum utensils to entertain VIP guests, while others were served with gold. Aluminum is also often confused with steel or silver because they all share a bright metallic appearance. However, unlike steel, which is heavy and magnetic, aluminum is significantly lighter and is completely non-magnetic. As for silver, although it looks quite similar, what we commonly call foil in everyday life is actually made almost entirely of aluminum, simply because real silver is far too expensive to be used in that way. Today, the world produces around 70 to 75 million tons of aluminum each year, while recycling tens of millions of tons from various sources. Notably, China, which accounts for more than half of global output, is accelerating recycling efforts as part of its strategy to reduce energy pressure and control emissions, with a scale more than 3 times that of the United States. In an era of rising energy costs, recycled aluminum is no longer just an environmental solution. It is becoming a force that is reshaping the entire global metal supply chain. The journey of aluminum's rebirth begins in places that are often overlooked: trash bins, scrap yards, and collection points across cities. Used beverage cans, discarded metal fragments from daily life and industrial production are gathered from multiple sources, ranging from households to industrial facilities. Thanks to its high recovery value, aluminum is rarely left behind. Instead, it is almost always reclaimed through recycling systems, scrap collection networks, or specialized recovery programs. After collection, the aluminum does not immediately enter processing plants. Instead, it is transported to intermediate consolidation facilities. Here, it is accumulated and compressed into large bales for easier storage and industrial-scale transportation. This marks a crucial transition, moving from scattered individual items spread across different locations. Aluminum is gradually consolidated into a large, unified stream of raw material, ready for the next stages of intensive processing inside recycling facilities. After being collected and transported to the recycling facility, aluminum enters the sorting stage, a critical process that determines the quality of the entire recycling chain. At this point, large bales of scrap aluminum are placed onto conveyor belts and pass through a series of automated separation systems. Magnets are used to remove ferrous metals, while eddy current technology helps separate aluminum from plastics, glass, and other non-conductive materials. Beyond that, aluminum is further sorted in detail according to alloy types and intended applications, such as beverage cans, industrial aluminum, or construction materials. Even slight differences in metal composition can affect the quality of the final product, making precision at this stage extremely important. Once sorting is complete, the aluminum is effectively material cleaned and ready for the next stages of processing. After sorting, the aluminum is fed into high-capacity crushing systems, where cans and metal fragments are cut and broken down into thousands of smaller pieces. Under the force of intense cutting and impact, the original rigid structure is completely broken apart, turning the aluminum into uniform shreds that are easier to process. This step does more than simply reduce size. It plays a crucial role in optimizing the subsequent stages. Once the aluminum is shredded, its surface area increases significantly, allowing processing to occur faster, more efficiently, and with lower energy consumption. At the same time, the improved uniformity and particle size helps ensure better control over metal quality throughout the recycling process. After being shredded, the aluminum moves on to a deep cleaning stage to remove any remaining impurities. Although it has already been sorted, the metal surface may still carry layers of paint, ink, grease, and organic compounds left from its previous use. The aluminum pieces are passed through thermal and mechanical treatment systems, where high temperatures help break down and burn off paint, printing ink, and organic residues. At the same time, additional separation and filtration systems remove any remaining ash and fine particles, leaving the metal surface cleaner and more uniform. This is a particularly critical step, as even a small amount of residual contamination can directly affect the quality of aluminum after melting. After impurities have been removed, the aluminum is transferred into industrial furnaces, where temperatures are raised to around 660 degrees Celsius, high enough to completely melt the metal. Under extreme heat, solid aluminum pieces begin to soften, deform, and gradually lose their original structure, merging into a glowing stream of liquid metal. During this process, aluminum is not simply melted, it also undergoes a form of refining. Lighter impurities such as residual paint, dust, and unwanted compounds rise to the surface as slag and are removed. At the same time, the high temperature fully breaks down old bonds, allowing the aluminum to return to a more uniform and purified state. Modern furnaces are designed to precisely control temperature and internal conditions, ensuring even melting, minimizing material loss, and preserving optimal quality. Once formed, the molten aluminum is kept in a stable state, ready for the next stages of production in the processing line. After reaching a molten and purified state, the liquid aluminum is transferred directly from the furnace into casting systems. Here, the glowing stream of metal is poured into large molds, where it begins the transition from liquid to solid. Depending on its intended use, aluminum can be cast into large ingots, thick slabs, or long billets, serving as intermediate raw materials for subsequent processing stages. This casting process requires strict control of both temperature and cooling rate. If cooling occurs too quickly or unevenly, the metal's internal structure may be compromised, leading to reduced quality. Conversely, when properly controlled, aluminum solidifies into a stable structure with the required strength and durability. As the molten metal gradually cools and hardens within the mold, aluminum once again takes shape, but this time, not as scattered fragments as before, but as uniform solid blocks of metal, ready for the next stage of processing. After the aluminum has been poured into molds and begins to solidify, the metal blocks cannot be removed immediately. At this stage, they are cooled with water, typically through continuous external water spraying systems that rapidly reduce the temperature and stabilize the internal metal structure. The strong flow of water strikes the red-hot surface, producing thick clouds of steam, a clear sign that the cooling process is actively underway. Once the temperature drops to a safe level, and the aluminum has fully solidified, industrial cranes come into operation. Massive cylindrical aluminum blocks, weighing several tons, are securely gripped by specialized mechanical clamps and carefully lifted out of the molds with high precision before being placed onto the factory floor. This entire process requires close coordination between machinery and technicians to ensure the blocks are not deformed or damaged during handling. At this point, the surface of the ingot still retains characteristic wave-like textures formed during solidification, while internal heat has not yet fully dissipated, meaning they must continue to be carefully monitored and controlled before moving on to the next stage. After cooling, aluminum slabs are fed into the rolling line, one of the most critical stages that directly determines the quality of the final cans. Here, the aluminum passes through a series of high-strength steel rollers where it is subjected to extreme pressure to gradually reduce its thickness. From blocks tens of centimeters thick, the aluminum is rolled through multiple stages, with each pass only slightly reducing thickness to avoid damaging the metal's internal structure. This process typically combines both hot rolling and cold rolling. In the initial stage, aluminum is rolled while still at high temperature, making it easier to deform and requiring less force. It then continues through cold rolling at lower temperatures, which increases strength, hardness, and improves surface finish. Between rolling cycles, annealing treatments are applied to restore the metal's ductility after it has hardened due to deformation. The result of the entire process is extremely thin aluminum sheets, typically around 0.2 to 0.3 millimeters thick for beverage cans, while still maintaining high strength, pressure resistance, and uniformity. These sheets are then wound into large coils, weighing up to tens of tons, and transported directly to production lines, where they will be stamped and shaped into finished cans. From these thin aluminum coils, the material enters high-speed stamping lines, where it is cut into circular discs and then deep drawn into the initial cup shape. From there, these aluminum cups are further stretched and thinned into can bodies through a drawing and ironing process, reducing wall thickness while maintaining the necessary strength. The rim of the can is precisely trimmed and formed to fit the lid, while the body is cleaned, printed, and coated with an internal protective layer to ensure food safety. Finally, the completed cans undergo a series of rigorous quality control checks, including tests for airtightness, structural integrity, and dimensional accuracy. They are then stacked and packaged in large batches, ready to be transported to filling plants. There, the cans are cleaned one final time, filled with beverages, sealed and labeled before being released to the market, appearing on store shelves as fully finished products, ready to reach consumers. Unlike most other materials, aluminum never truly reaches the end of its life cycle. It simply keeps transforming from one form to another, again and again. With each recycling cycle, aluminum not only retains its original quality, but also saves a tremendous amount of energy compared to producing it from raw materials. This is what makes aluminum one of the most sustainable materials ever created, where the concept of waste almost doesn't exist, but instead marks the beginning of yet another life cycle. Few people realize that glass, an everyday familiar material, is placing growing pressure on global natural resources. Creating it from scratch comes at a high cost. Billions of tons of sand are dredged every year, causing severe erosion and damage to river ecosystems. Beyond the massive energy consumption and CO2 emissions, impurities in raw sand are also a #1 enemy, aggressively corroding the refractory bricks of million-dollar furnaces. That is why glass recycling has become a key solution for preserving this precious resource. Environmental leaders such as Switzerland and Germany have now reached recycling rates of up to 90%, 3 times higher than that of the United States. Why do you think this enormous gap exists? Many people wonder whether recycled glass is truly clean enough for food use, but the truth is that it is just as pure as new glass. Unlike plastics or rubber, which can easily undergo structural changes, glass is completely inert. It does not absorb odors, does not retain color, and most importantly, does not release any microplastic particles into the human body. That is why, at the strictest frontiers, such as vaccines and high-grade pharmaceuticals, the world still has no perfect substitute for glass, a gold standard for human safety. And now join us as we explore this remarkable rebirth. A journey that may seem vast in scale, yet begins in the simplest of places, the household waste bins of millions of families. For this circular process to begin, the first requirement is a stable supply of used bottles and jars. In modern recycling systems, collection largely relies on fleets of specialized trucks, machines designed exclusively for glass. On average, a major operator such as Biffa in the United Kingdom must cover around 3,000 households per day to ensure not a single fragment of recyclable glass is left behind. This pressure becomes even more intense during the summer months, when warmer weather drives up demand for cold beverages. The resulting surge in discarded bottles and jars forces collection trucks to operate at full capacity, making multiple collection rounds per day instead of the usual single run. But door-to-door collection is not the whole picture. In most EU countries, networks of reverse vending machines are now installed throughout supermarkets, activating source-level sorting right at the point of disposal. Consumers simply place an empty bottle into the machine. The system scans it, sorts it, and returns a small cash refund, typically around 10 to 25 cents, depending on the country. A soda bottle you've just finished drinking, instead of becoming waste, can instantly turn into loose change for your next purchase. This approach not only encourages people to participate voluntarily in collection, but more importantly, it supplies recycling plants with a stream of pre-sorted, cleaner, and far more uniform glass than ordinary mixed waste. From here, the journey of transporting tens of tons of bottles and jars to specialized processing plants begins. Large trucks, each capable of carrying between 20,000 and 30,000 bottles per trip, operate continuously, moving between supermarkets and collection points to consolidate the material for recycling. The processing cycle is formally initiated when heavy-duty industrial loaders move in on stockpiles of waste glass rising several meters high. Each bucket can hold multiple tons of material, which is transported in a controlled manner across the yard to maintain a steady feed rate into the plant. At the intake point, the glass is discharged directly into receiving hoppers. Driven by gravity, the mixture of fragments slides down reinforced steel chutes where conveyor systems come into operation. From this moment on, the glass stream, still mixed with sand, dust, and contaminants, is carried deep into the processing line, where successive stages of cleaning and sorting will ultimately determine the quality of the entire downstream recycling process. After being broken down, the waste stream makes its first stop at a multi-stage vibrating screening system. Here, high-frequency vibrations separate natural contaminants, such as dust, gravel, and sand, from the main glass flow. This stage serves as a surface cleaning step, allowing the material to be more clearly exposed and prepared for more advanced sorting processes. However, mechanical equipment at this stage cannot fully remove larger or lighter contaminants, such as paper labels, plastic films, or pieces of wood. As a result, a manual inspection zone follows immediately after the vibrating screens. Specialized workers are positioned along the conveyor belt to visually monitor the stream and manually remove any remaining foreign objects. The combination of mechanical separation and human judgment ensures that the material meets cleanliness standards before entering the more sophisticated downstream separation systems. But even after screening and sorting, troublesome obstacles always remain hidden within the pile of broken glass. Bottle caps. These are the enemies of the furnace, as they do not melt like glass and instead introduce contaminants capable of ruining an entire batch. At this stage, massive electromagnets suspended above the conveyor belt come into operation. Generating extremely strong magnetic fields, they lift and extract every steel bottle cap or screw upward, completely separating them from the glass stream moving below. Thanks to this decisive step, the cleanliness of the material is raised to around 80%, clearing the way for the critical crushing stage that follows. Once most contaminants have been removed, the glass enters a critical stage of structural transformation. Crushing. Large fragments are fed into hammer mills where high-speed rotating hammers deliver repeated impacts, breaking the glass down into uniformly sized particles. To maintain quality control, any pieces exceeding the specified size are captured by screening systems and redirected back into the crushing chamber. The result is glass cullet with a fineness comparable to manufactured sand. Reducing glass to this granular form not only allows it to melt more quickly in the furnace, but also helps save up to 40% of the energy required compared with using entirely virgin raw materials. Immediately after crushing, the material stream is passed through a high-capacity extraction system. Here, powerful air currents strip away and blow off any remaining microscopic label fragments still clinging to the surface. This final cleanup step ensures the glass reaches maximum purity before entering the laser-based sorting stage. The final, and also the most sophisticated stage in the cleaning process, is optical sorting. At this point, glass fragments are spread thin and allowed to fall like a waterfall in front of a system of high-power laser sensors. In a split second, these sensors scan each fragment to accurately analyze its color and material composition. As soon as a differently colored piece of glass is detected, or more dangerously, a stray piece of ceramic, the system immediately activates compressed air nozzles. These air jets fire with millimeter-level precision, blowing the contaminants out of the main stream in just milliseconds. Absolute precision at this stage is vital, because even a tiny amount of color deviation or ceramic contamination can completely ruin the transparency and quality of the entire batch. After passing the laser system's inspection, the clean glass fragments move along the conveyor belt to the final collection area. Here they are separated and stored individually according to 3 color codes: clear, green, and brown. A step that may seem simple, but in fact directly determines the value and efficiency of recycling. Few people know that clear glass accounts for the largest proportion and has the highest economic value. However, with just 1% colored glass mixed in, a melting batch will immediately become cloudy and unable to regain its original transparency. Therefore, color separation is mandatory to control purity, enabling factories to recycle directly into new products of the same type without incurring the cost of removing color impurities. After being refined, recycled glass cullet cannot be fed directly into production, but must first go through a raw material blending stage. The basic composition starts with pure silica sand to ensure transparency. Next comes soda ash to lower the melting temperature, and limestone to increase the mechanical strength of the finished product. Depending on specific requirements, manufacturers add minerals such as alumina, dolomite, or metal oxides to adjust color and physico-chemical properties. In this batch mixture, recycled glass accounts for 20 to 70% of the total weight. This proportion allows the mixture to melt faster, directly saving about 40% of operating energy and reducing carbon emissions compared with using only virgin raw materials. Once the components reach the standard proportions according to the preset formula, the mixture is thoroughly blended and moved to the melting stage. The batch is fed into a high-capacity gas-fired furnace system. Here, the temperature is maintained at around 1,250 degrees Celsius to carry out the material transformation process. Because the heat radiated into the surrounding environment is extremely intense, the operating crew must wear specialized heat-insulating protective clothing and thick gloves to control the melting pot safely. After about 24 hours of continuous firing, the raw material mixture melts completely and turns into a highly viscous liquid. During the next 5 hours, the molten glass is kept at a stable temperature for the refining stage. This is a mandatory step that allows air bubbles to escape, ensuring the purity and uniform structure of the glass stream. To transform the molten glass stream into products with specific shapes, the mold system is an indispensable component. Based on designs created in specialized CAD software, molds are manufactured from cast iron or special alloy steel. These materials possess extremely high heat resistance, up to 1,400 degrees, ensuring they do not deform when in continuous contact with molten glass. After fabrication is completed, the mold sets are installed on the production line, ready for the forming stage carried out directly inside them. When the mold system is ready, the process enters the double blow stage, the standard method for producing hollow containers such as soft drink bottles or pharmaceutical jars. The process begins by cutting the molten glass stream into gobs of uniform weight. These gobs enter the preliminary mold at around 1,000 degrees Celsius, the ideal temperature at which glass reaches stable viscosity, allowing smooth forming. Inside the preliminary mold, a first blast of compressed air is blown forcefully from above, pressing the molten glass tightly against the mold walls. The result of this step is the formation of a parison, a hollow structure in which the bottleneck is clearly shaped, while the body remains soft and retains a large amount of heat. Immediately afterward, the glass parison is transferred to the final mold set, located right next on the production line. Here, a second blast of compressed air is injected directly into the center of the parison, stretching the softened glass outward until it fully conforms to the fine details inside the mold cavity. Although this process appears very fast from the outside, in reality, the entire system of valves and sensors must be synchronized with precision down to 1/1000 of a second. It is precisely this extreme level of technical control that enables corporations such as Coca-Cola or Heineken to ship hundreds of thousands of bottles every day with absolute uniformity, ensuring that every single bottle meets the same standards before global distribution. Although today glass packaging accounts for only about 15% of Coca-Cola's total output, it is by no means outdated. On the contrary, for many discerning consumers, glass remains an irreplaceable choice. It keeps drinks cold longer, does not retain odors, and does not alter flavor. As a result, the fizz and sweetness are preserved intact, a purity that plastic or aluminum has yet to fully replicate. While China dominates the world with more than 50% of global pencil production, operating like the planet's gigantic manufacturing machine, on the other side of the hemisphere, Brazil has emerged as South America's pencil superfactory, home to the largest Faber-Castell facility in the world, where forests are transformed each day into millions of writing instruments distributed across continents. Yet behind these impressive figures lies a fascinating paradox. Pencils have never actually contained lead. The familiar name originated from a 16th century misunderstanding, when graphite was first discovered and mistaken for the metal lead, an error that persisted for hundreds of years. And it is precisely that simple carbon core that creates something remarkable. A single small HB pencil can draw a line up to 56 kilometers long, roughly the distance from downtown Los Angeles to Disneyland Anaheim. To understand why a small pencil stands behind a multi-billion-dollar industry, we must return to where the story truly begins, not in the factory, but in the forest. Each year, billions of pencils are produced, creating an enormous demand for carefully selected timber from across the planet. The forests of California red cedar become the ideal starting point, where straight, soft, and dimensionally stable trunks are cultivated for 20 to 30 years for one single purpose: to become humanity's writing tools. Massive old-growth trees with trunk diameters reaching 100 centimeters are typically felled using high-powered chainsaws. Meanwhile, smaller trees are gripped by modern harvesters that cut them at the base, strip away their branches, and section them into logs within seconds, faster than the blink of an eye. In the heart of the wilderness, steel, hydraulics, and roaring engines merge together, turning the forest into a colossal raw material production line operating without pause. Once felled, the journey of the timber has only just begun. In remote and rugged terrains where no roads exist, logs are airlifted by specialized helicopters, lifting massive trunks off mountainsides like enormous cargo suspended in midair. In most industrial forests, however, giant mechanical arms clamp onto each trunk, bundle them together, load them onto heavy-duty transport trucks, and move them along forest roads built specifically for the logging industry. Convoys of timber roll through dense woodlands, cross the icy landscapes of the northern regions, pass over great rivers, and eventually reach seaports, where they continue their voyage aboard colossal cargo ships sailing across oceans. After standing still in nature for decades, these tree trunks now become passengers in a global logistics network, bound for processing plants where the story of a pencil is truly written. While timber leaves the forest to become the pencil's body, elsewhere on Earth, its soul is awakened from beneath the ground. If wood forms the outer casing, graphite is the spirit that writes every stroke, two separate materials converging to create a complete pencil. This mineral is primarily extracted from open-pit mines in China, Brazil, and Mozambique, nations with abundant reserves and relatively low extraction costs. To reach graphite veins buried deep underground, miners descend into dark tunnels where sunlight barely exists. They ride industrial elevators hundreds of meters below the surface, set fuses and explosives, then retreat nearly 300 meters before the earth trembles violently. When the blast subsides, they return through clouds of dust and shattered rock to collect the glossy black graphite blocks. Heavy ore carts are hauled back to the surface using industrial lifts, where even a brief power outage can transform routine work into a life-threatening challenge deep underground. At the surface, the graphite is crushed and processed to separate pure carbon crystals from impurities such as soil, rock, and metal. The result is high-purity graphite powder, often exceeding 90% carbon content, ready for the next stage, forming the pencil core. As timber arrives at factories and graphite travels across continents, the two materials finally converge to form the perfect structure that protects and carries the writing core. From this point on, the crafting process truly begins. Inside the workshop, massive wooden beams are fed into automated sawing systems, where laser beams and infrared sensors continuously measure straightness, density, and grain patterns in real time. Only sections that meet strict standards are sliced into slats 5 to 6 millimeters thick, the ideal dimension to create 1/2 of a pencil body. A deviation of just 0.1 millimeters can cause the pencil to break or sharpen poorly. Each cut is therefore not merely machining, but a precise transformation, the moment a tree trunk begins its evolution into a writing instrument for humanity. After cutting, the wooden slats pass through multi-blade automatic grooving systems. High-speed rotating cutters carve uniform longitudinal channels with tolerances measured in thousandths of a millimeter. A misalignment no wider than half a human hair could throw the graphite core off balance and cause the pencil to snap the moment it is sharpened. While the pencil body is being shaped, on another production line, the graphite core is undergoing its own transformation to become the true heart of the pencil. To create the writing core, graphite powder is blended with clay in ratios so precise that major brands like Faber-Castell and Mitsubishi Pencil guard their formulas almost like high-end perfume recipes. The more clay added, the harder the core and the lighter the stroke. The more graphite included, the softer and darker the line. This is why familiar markings such as H and B appear on pencil barrels, details many people rarely notice. H, hard, is used for technical drawings requiring fine lines. B, black, is preferred for bold artistic shading, and HB represents the balanced middle ground. Next, the cores are dried to remove moisture, then fired in kilns at temperatures reaching 1000 to 200 degrees. This process stabilizes their structure and increases hardness. Finally, the cores are soaked in oil or wax to reduce friction, allowing for smoother writing and less dust during use. Unlike standard pencils, colored pencil cores contain no graphite at all. Instead, they are made from pigments blended with wax or oil, materials that, in the history of fine art, were once more valuable than gold. Each shade of red, blue, or yellow carries its own precise pigment wax-oil ratio, because every color particle reacts differently to light and friction. This means that a box of 120 colors represents 120 independent material formulas. The mixture is thoroughly blended, extruded into strands approximately 17.5 centimeters long, dried, and then tested for color accuracy and brittleness before being inserted into the wooden casing. Because colored cores are not fired at high temperatures like graphite, they remain softer and more fragile, requiring transportation and assembly processes executed with near handcrafted precision. Once completed, the graphite or colored core is precisely placed into the pre-carved grooves using a high-accuracy automated system. A second wooden slat, coated with specialized adhesive, is then laid on top, firmly enclosing the core in the middle to form the well-known wood sandwich structure, a design that originated in the 18th century and has endured to this day thanks to its exceptional stability. The entire wooden block is then subjected to hydraulic pressing with forces reaching up to 5 tons, ensuring the core remains perfectly centered and durable throughout the pencil's lifespan. From that moment on, wood and core are no longer separate components, but fused together as one, officially becoming a complete pencil. After the wood sandwich block is fully stabilized under pressure, it moves into the shaping stage. The long wooden strips are cut into standard 17.5 centimeters lengths, then fed through high-speed milling systems to form their final shape. Most commonly the hexagonal design, which prevents rolling, saves material, and provides a more balanced grip for extended writing. Next, each pencil undergoes strict quality control. Cameras and precision sensors detect off-center cores, microscopic cracks, or abnormal vibrations before the product is approved for market release. After shaping, the pencil enters the coating stage. Each one is finished with 3 to 6 layers: primer, color, and a final protective coat. The iconic yellow, long associated with pencils, was originally used to promote Chinese graphite, considered the finest in the world during the 19th century. Today, manufacturers also use red, black, blue, or even natural wood finishes. The paint is not merely decorative. It protects against moisture, prevents decay, and allows the barrel to withstand thousands of sharpenings without cracking. Once fully dried, the pencil moves to the branding stage. High-speed printing machines stamp the brand name, product code, and hardness grade, such as HB, 2B, or H, onto the barrel, part of a classification system that can include more than 20 distinct levels. A single small marking determines whether the pencil is suited for everyday writing, technical drafting, or artistic sketching. In the final stage, many pencils are fitted with the savior of every writing mistake, the eraser. The metal ferrule is stamped from thin coils of aluminum or brass, forming small ridges that grip the barrel tightly. Inside sits an eraser made from synthetic rubber, blended with softening agents and ultra-fine abrasives, designed to lift graphite cleanly from the paper. The entire ferrule and eraser unit is then automatically crimped onto the end of the pencil by precision machinery. For pre-sharpened pencils, the last step is revealing the writing core. Industrial sharpening machines with fixed blades create an almost perfect angle, ensuring smooth, consistent lines from the very first stroke. Sensor systems automatically adjust the cutting depth based on the hardness of the core to prevent breakage. Before leaving the factory, every pencil must pass a final inspection: barrel straightness, core alignment, paint consistency, and the firmness of the eraser. Only those that meet strict standards are sorted and packaged into boxes of 6, 12, or 24, in recycled paper sleeves, clear plastic cases, or even premium tin boxes. From distribution centers, they are shipped across the globe. Remarkably, an average pencil can write more than 45,000 words or draw a line up to 50 kilometers long. From classrooms and laboratories to art studios, billions of human ideas begin with nothing more than a single stroke of graphite. At modern sugar mills, thousands of tons of cane are received each day and moved into the pre-processing area. All incoming cane is accumulated on large storage yards or continuous conveyor systems. When processing begins, the cane is fed into intake hoppers and directed toward the primary handling equipment. Before pressing, the cane passes through a high-pressure water spray system that thoroughly removes dust, soil, and any surface impurities. Tiny grains of sand, seemingly harmless, can wear down the steel rollers and damage an entire multi-million-dollar mechanical line. The wash water is then recovered and treated in a closed-loop system, because even a small amount of bacterial contamination can cause the juice to ferment prematurely, ruining the entire batch of sugar from the very first stage. This is why the washing step, though simple in appearance, plays a critical role in the whole sugar production process. After the cleaning stage, the freshly cut cane is fed into the shredding system. Here, high-speed rotating knives continuously cut, slice, and tear open the tough outer rind while breaking down the inner fiber structure. This process softens the cane, increases its surface area, and exposes the sugar-bearing fibers within. By loosening the material and opening the cell walls, the shredder ensures that the downstream crushing mills can extract juice far more efficiently and with maximum yield. Next, the entire stream of material moves into massive, multi-roller crushing mills, equipped with a multi-stage roller assembly operating on a progressive compression mechanism under immense pressure. From here, a curious separation begins. The sweet cane juice becomes the next raw material for producing sugar, the white gold that sustains an entire industry. What remains, dry, fibrous, and seemingly lifeless, is the bagasse. Yet with modern technology and a new mindset, these discarded fibers are now collected and reborn, beginning a different journey, where waste is no longer the end of the story. Right after the juice is fully extracted at the sugar mill, thousands of tons of dry bagasse are gathered into massive outdoor piles. In countries where the sugar industry operates year-round, these bagasse hills can reach 5 to 6 meters in height and stretch across hundreds of square meters. The drying process may seem simple, but it is an extremely critical step. Excess moisture, if not removed properly, can cause the bagasse to rot, develop mold, or even ferment, leading to losses of tens of thousands of dollars. With natural sunlight and good ventilation, this drying period can last from several hours to a few days, depending on the weather and the thickness of the pile. Once dried, the bagasse is collected using loaders or conveyor systems and transferred onto specialized trucks. From there, it is transported to recycling facilities or biomass processing plants, where the material is revived and transformed into higher-value green products. At the recycling plant, the bagasse is received and carried directly inside through a continuous conveyor system. The first step, and one of the most critical, is cleaning the material. Here, the bagasse passes through a high-pressure water spray system to remove soil, sand, shredded cane fragments, and any remaining sugars clinging to the fibers. After washing, the material is mechanically dewatered or lightly dried to reduce its moisture content, creating ideal conditions for the subsequent grinding stage. The milled bagasse fibers are heated to 130 to 180 degrees Celsius, then blended with a small amount of natural starch or recycled pulp to improve flexibility and prevent cracking. Even in tiny quantities, these additives are key to turning the fibers into a strong, mold-ready biomaterial. After the refining process, the semi-liquid bagasse mixture is fed into specialized metal molds, preheated to 160 to 200 degrees Celsius. These molds are engineered with absolute precision for each product shape, from spoons and food containers to cups. When the mold closes, high pressure compresses the mixture into its final form, creating a solid structure through heat and compression alone, without the need for any chemical adhesives. When the hot pressing stage is complete, the product has taken shape but remains soft and firmly attached to the mold. It is sprayed with high-pressure cold water to cool it rapidly and assist with demolding. The entire mold set is then immersed in a vibrating water bath, where swirling currents cool the product completely and allow it to release smoothly from the mold without cracking or warping. After being dried to stabilize its moisture content and increase surface rigidity, the product becomes fully formed, sturdy, and ready for the trimming stage. At this stage, the excess edges formed during hot pressing are cleanly removed using specialized trimming blades. These high-speed cutters are calibrated for each mold design to ensure sharp, precise cuts without distorting the product's structure. The edges are then smoothed either by automated machinery or by skilled workers, eliminating any remaining fiber burrs, small details that can affect handling comfort and overall safety. In more advanced facilities, this entire process is fully automated through robotic systems. Integrated cameras and optical sensors continuously scan the product's surface, detecting even the slightest irregularities along the outline. The robot then adjusts cutting force, angle, and speed in real time, creating perfectly consistent edges that manual trimming could rarely achieve. Skipping this step would leave sharp or uneven edges on the product, compromising not only its visual quality but also its safety. Such imperfections can tear packaging during transport, scratch the user's hands, or create discomfort when the product comes into direct contact with food. For these reasons, edge trimming is an indispensable stage to ensure the final product meets rigorous standards of quality, safety, and user experience. Finally, the surface of each product is coated with a bio-based waterproof layer made from plant waxes or natural polymers. This ultra-thin coating allows bagasse items to withstand high temperatures, oily foods, and even liquids without absorbing moisture, softening, or deforming, an advantage conventional paper products simply cannot offer. Next, every plate, spoon, or container passes through a quality control system before being counted, sorted, and packaged by workers using recycled paper or cardboard to minimize environmental impact. From the production line, these items, once nothing more than agricultural waste, are shipped to supermarkets, restaurants, and food outlets around the world, where they replace single-use plastics with a solution that is sustainable, safe, and emblematic of modern green innovation. Have you ever wondered why products made from bagasse feel as sturdy as plastic while still being environmentally friendly? The secret lies in the way cellulose fibers naturally bond with one another under high heat and pressure, forming a kind of bioadhesive created right inside the mold. In theory, products made from bagasse can fully biodegrade in just 60 to 90 days, an impressive figure compared to traditional plastics, which can take 500 to 1,000 years to disappear from nature. But the reality is more complex. This rapid biodegradation occurs only under industrial composting conditions.